Hello everyone, welcome to the video for the Algebra 2 Chapter 5 End of Course questions. And if you don't remember, the end of course is that big state test that you take at the very end of the year. And you may also have some questions on your Chapter 5 test as well. So let's look at question number 1. What they want you to do is interpret what looks to be an exponential decay. So remember, when you have an exponential growth or a decay or a logarithm, when it's graphed, you're going to have some sort of asymptote. And typically the asymptote is on the x-axis. But you can see that it is not getting closer to the x-axis. It is actually getting closer to this line right here. Okay, so that's kind of important because the x-axis in this case represents 0. So let's read what are the different situations and then which one is going to apply. So it's asking specifically, what could the vertical axis represent? So it's going to be the height of a growing tree. Well, now if it's going to grow, wouldn't it start here at 0 height and then just kind of go up? Yeah, so it's not going to be A. The speed of a car as it coasts to a stop. This word is really important because if something's actually truly going to come to a stop, it would actually get closer and closer and hit the x-axis. So it doesn't get there. The temperature of a boiling cup of water sitting at room temp. Now this one makes sense. So this is how much it's going to be when you sit it down. It's boiling, it's going to cool off, and then this right here is your room temperature. So anything that's cooling off is going to have that exponential decay, and if it's cooling to room temperature, that asymptote is going to be above your x-axis. So C is definitely what we're looking for. Now, I do want to talk about D. It says the temperature of an ice cube sitting at room temperature. So an ice cube, what an ice cube will do is it's going to warm up. Now, it might warm up and it might do something like this right here, and it's going to approach room temperature from the other direction, which is logarithmic. Question number 2. A movie theater sells 437 bags of popcorn on opening night. So that tells you start with 437 bags. The theater manager predicts that on the second night, the popcorn sales will be 85%. So that tells you that you're going to have less sales on the second night. That is going to be a decay because you are changing by multiplying by 0.85. Anytime you change via percent, that is going to be an exponential change, could be growth or decay. What is the most appropriate estimate of the amount of popcorn on the second night? Now, if it wanted you to do something like maybe 7 nights, 8 nights, 100 nights past, then I would write a formula. You don't need a formula. So what I would do is I would just start with 437 bags, and all you have to do is calculate 85% of that amount. Just multiply the two. Make sure you use the proportion, 0.85. When you multiply them, you get 371.45 bags. And if you look, see how it's asking you the most appropriate estimate. If somebody wanted to know how many bags that you've sold, that can only be a whole number. So it's either going to be 370 or 371. It's going to round down to 371 bags. Question number 3. And I apologize if you may have gotten part of this question clipped out of your paper for a hole punch, but this is what it looks like. It says, which property was used to rewrite this equation? Let me go ahead and write it down over here so you can kind of see what happened. Okay, so what you've got to do is you've got to figure out what changed between the first step and the second step. 2 to the power of x is the same, but the minus 7 isn't there anymore, which means that they had to do the opposite. They had to add 7 to both sides. So when you're adding 7 to both sides, that's just the addition property of equality. Question number 4. A student is solving the equation. I'm not going to read it. The table shows the student's steps. So this is a very typical question that they ask on equations that are complex enough. They don't want you to just give the answer. They want you to be able to see patterns and recognize steps. So what we're going to do is talk about what's changing between each step. You can see that this 8 has changed into 2 to the power of 3. So that's just one of those techniques that you use to write the same base for both sides. So this is correct. 2 to the power of 3 is 8. So we have step 1 is good, step 2 is good. Now, when you do that, you have to deal with this section right here. To properly deal with that, you have to distribute the 3 to x minus 2. And they did not do that in this line right here. They should go 3 times x, and then 3 times 2, that should be 6. So that is the mistake. The error is not distributing. And it says which 2 steps does the student make a mistake? It's between step 2 and step 3. And if you start to see some of these questions more often, that means that they are very likely to be asked on tests and benchmarks and EOCs. So question number 5 is another example of this. They give you one of these base equal a base questions, and they're asking you what was the mistake. And there's definitely a mistake. If you can see here, you've got 16 has been rewritten as 2 to the power of 4. 2 to the power of 4 is 16, so that does check out. But you've got to remember, you have to multiply when you have a power to a power. So you have to do 4 times 2x. 4 times 2x should be 8x. So we've got our mistake right here. And what are they asking us? Made the first mistake in step number 2? Yes, that is it. So you don't necessarily have to solve all of your equations. You do have to understand how to solve them by hand, though. Question number 6. Which of these is the asymptote of the graph of the function y equals log base 12 of x? For you to fully master this unit, you need to really truly understand all of the different graphs between exponential decay, growth, logarithmic growth, and decay. So let me remind you here. Exponential decay is always going to have an asymptote on your x-axis, and it will hit on the y-axis at 1. Growth is similar. It will have an asymptote in the same spot. It will also hit at 1, but it will grow. So this is growth, and this is a decay. And it doesn't matter what base it is. So if you look here, the base in this particular question is 12. So if it was 12 to the power of x, it would grow. It would still hit at 1. Okay, so that is 1 on the y-axis. Let's look at logarithms. Logarithms are the inverse of exponential. So an exponential decay, it's still going to look like a decay, but it's going to hit here on the x-axis. So everything trades. So it's going to hit the x-axis at 1, but instead of having an asymptote on the x-axis, it has an asymptote on the y-axis. This is a logarithmic. This is exponential, and these are logarithmics. This is also a decay. And then this one is going to have the same y-intercept. It's going to have the same x-intercept, but it is going to grow instead in that manner. Okay? So if you look here, we have a logarithm. It's going to be one of these bottom 2 graphs. It has a base of 12. If your base is greater than 1, it's going to grow. So, and it honestly doesn't matter because they both have an asymptote, which is what you are looking for, of the y-axis. So your answer to question 6 is B. Question 7. Now, if you want a little bit of a break, if you're really good at transformations, this question's for you. You can see that we have transformed a logarithmic function. It has base 8, so it should grow. So a logarithm that grows is going to look like this. at the beginning. Now this one, on the other hand, has some transformations. This one is going to make it go left. No. I almost missed it. Right 2. And this is going to make it go down 4. So what we're going to do is we're going to track this right 2 and down 1, 2, 3, 4. No. Ooh, I'm skipping. So right 2, 1, 2, 3. There it is right there. See how it hits perfectly? So that is the second choice, which is B. Another thing you need to be able to do to master this unit is to be able to give either a growth rate or a decay rate. A decay rate is dangerous because a lot of people don't pay attention. And this one is a decay. I think you guys are really good at telling whether or not something is a decay versus a growth. This is a decay because the base is between 0 and 1. But kind of the knee-jerk reaction is that you guys are going to say this is an 85% decrease. This is not true. 99.9% of cases, it's never what you see. So if you see a rate or something that looks like 0.85, it's what you're keeping. So you are keeping 85%. If you're keeping 85%, then what are you losing? You are losing 15%. Now that's how you do it mentally. So the answer to this question is D. No, it's not. It's B. Mathematically, what they're wanting you to do is they're wanting you to rewrite this as a decay using 1 minus R. So if you were going to rewrite 0.85 as 1 minus any number, just use your calculator. 1 minus 0.85 gives you 0.15. And then now you can see it. So if it's not written in that 1 plus or minus R form, you can't really see the growth rate or the decay. So question 9 is a very typical end of course question. There's a lot of words, a lot of extra information in there. Please don't let that make you think it's more difficult. This one is actually a little easier than the last one because number 1, this is a growth. And number 2, they actually write it in that form that you want it to be written in. Do you see how they changed the 1.038? They changed that to 1 plus 0.038. So what you can do is you can very easily see the growth rate. So I'm going to go ahead and just get rid of anything that says it's decreasing because those are definitely not going to be it. And it has to grow by this much. You've got to change that to a percent, and that is 3.8%. And you notice one of these choices is a decimal off, so do not choose the wrong percent. Okay, so this question number 10 is similar to the last two, except for it is a short answer format, and that's possible on your benchmark, your tests, and your end of course. We've got a new function here. We have an initial amount of 100, and then we have a rate. It looks like we have it's a decay because it's between 0 and 1. So remember, your answer is very rarely going to be that 0.87. If it's a decay, it's about what you're losing, not what you're keeping. So if you're keeping 87%, what are we losing? So mentally, if you can do that in your head, you're just going to quickly say, well, that's 13%, and that's correct. Okay, but mathematically, what you should be kind of doing, this is what you're doing in your head anyway. Instead of writing 0.87, you have to write it as 1 minus what number? So in your calculator, 1 minus 0.87 gives you 0.13, or that should be H. And then now you can see it. So it doesn't matter to me if you do it 1 minus or if you just do it in your head. Okay, so question number 11 is more advanced in 2 different ways. You have to be very good at parent functions. And you also have to be very good at reading questions like this and understanding what they're asking you to do. Notice that they have immediately told you that we have 2 different functions. Sometimes people think that if they give them an equation and you see a table, they are the same function. This is not the case. So you have, I'm just going to call this the yellow function here. You can see right here that it is a growth because your base is E, and E is bigger than 1. So this is an exponential growth. What does an exponential growth look like from the parent graph perspective? It hits at 1, and it goes up like this. Now, this is obviously not a parent graph because it has been shifted in some way. So plus 6 on the x is going to make this one actually go left 6. So I'm going to count 1, 2, 3, 4, 5, 6. And I'm going to do the same thing. But that's kind of what it looks like, okay? It's still not going to touch that x-axis. So what that does is it tells me that all of my x values, all of these inputs, no, your x values can be negative, but all of your output values, all of your h of x values are going to be positive. So remember, x is your input and h of x is your output or your y values. So these are all going to be positive. That's going to come into play in a second. All right, now let's look at the table. So the table, that is that blue function, that's j of x. Now if you look, this is really close to 0, a little bit bigger. It's hitting 1 here. It hits 1 at 0. Well, that sounds familiar to me. So it's really little, and then it's getting bigger and bigger and bigger. So this table is showing exponential growth. So both of these are exponential growths. They might have different bases, but they're exponential growth. So regardless of what your x values are going to be, your output or your y values are going to be positive. So that answers our question for us. It says h of x and j of x are positive. So the y values are positive for your x values. And this is true. And I know it's true because they don't go below the x-axis. They don't touch the x-axis. So that is an advanced question, and that is how you do that one. Okay, question number 12. You really have to pay attention to the details in the instructions because this one looks like question 11, but it is different. It actually gives you the equation of g of x, and then it also shows you the values of g of x. So this is the same thing. They are not talking about two different functions this time. So what I'm going to do, I'm actually just going to use transformations. I don't really need the chart or that table. I do know that this is a log base 10. It's a common log. So that means it's going to grow. It's going to hit about right here. And it's going to hug that y-axis and get a little bit bigger like that. So that's the parent graph. But on this one right here, this one, you see how it says -2 from the x. That means it's going to go to the right 2. So I'm going to shift this 2 places. So now my asymptote, let me use a different color. Asymptote is right here going down the y-axis. But if I shift this, it's also going to shift the asymptote. So now I'm going to hit here at 3 instead of 1, and it's going to go up like that. I can tell that just from transformations. Now, if you don't remember the transformations of the parent graph, then you can use this to figure it out. So this is what it's looking at. I'm going to look only at the orange graph. I'm going to get rid of that one and answer the question. So as x approaches negative infinity, x actually doesn't approach negative infinity. X stops at 2. So this is not an option. As x approaches positive infinity, so as it goes to the right, it actually increases to positive infinity. It does not approach 1, so B is out. As x approaches 0, x does not approach 0. As x approaches 2, yes, x does approach 2 from the right side. It keeps approaching. It's getting closer and closer. This is x equals 2. It's getting closer to it. And that's the asymptote. So that is definitely advanced, but you do have the ability to answer that question. So question 13 is great if you're really good at transformations. What it does, though, is it shows the transformation using function notation. And function notation is generic for any function, so it really doesn't matter what function they give you at the beginning. You can kind of tell right here when it says x minus 1, if you're taking away from x, that means you're moving it to the right. And what we're trying to do is we're trying to figure out who is correctly describing the transformation. And if this says -1 here, we're supposed to be going to the right. So this is incorrect. Negative in front of your function, that is a reflection over your x-axis. Look what they put. And they put the y-axis, so that is incorrect. -3 from the functions, typically at the end of the equation. 3 units down, yes. Okay, so that one is correct. So that is the answer to the question. Let's talk about why this one is not. That one should be left 4. You see how they say 4 units up? No. So student 3 is correct. Okay, question 14 should look familiar to you. It's got 2 different functions. They look like they are both exponential growths, but it looks like one is above the other. So if you look underneath it, it gives you the function for f of x, and then it says g of x has been manipulated. Like these are the same, except for g of x has changed. Well, yeah, it's obviously changed. So the easiest way for you to tell how an exponential growth has changed is look at the y-axis. So as you can see, the asymptote has moved down. So this is also 1, 2, 3. This is 4. So it has moved 1, 2, 3, 4 down. And 4 down means that you're supposed to subtract 4. All right, question 15. You're going to have to draw some information from your last chapter, 1-to-1. So 1-to-1, we talked about it. You're actually really good at it. It's just been a minute. It's when it will pass, the graph will pass both the vertical line test and horizontal line test. Okay, so let me remind you. Also, you got to know your parent graphs. So if you don't know that x squared looks like this, if you have a calculator, graph it, that's great. But if you don't, I don't know what to tell you. So you got to know some of your parent graphs. So x squared is going to look like this. Does it pass the vertical line test? Yes. So if I'm just scanning it vertically, it is good. But if I scan it horizontally, remember, it's not supposed to touch any of those lines more than once. So this one is not 1-to-1. So that is the answer to it. Let's talk about why the other 3 do fit. This is exponential growth. Exponential growth looks like this. It will pass both this. Oh, I didn't mean to do that. And that. So that passes 1-to-1. What does the square root of x look like? It looks like this. It will pass both the vertical and the horizontal line. And log of x is very similar to the square root. So it will pass both of those as well. But we're looking for the one that was not. All right, question 16 is for my honors group, but everybody can still do it with little to no explanation. All right, here we go. So the first thing you want to do is you want to swap them out because you're doing the inverse, obviously. If you're not in honors, you're not going to understand this. That's called a power property. We're going to put the 7 in the front. I'm also going to write this invisible little base e here. I've got to get y by itself, and y is part of the logarithm, so that means divide by 7. So if you don't have x divided by 7 in the problem, yeah, I've already kind of, like, I know what that looks like. But let me tell you why that's the answer. You're going to change it to logarithmic form. So you're going to do base e to the power of x over 7 is equal to, oh, I forgot to write the y. is equal to y. So there you go. All right, so they're wanting you to solve for x. You can absolutely do this using Desmos, but I'm going to pretend that we don't have access to Desmos. I'm looking at clues here. The 3 and the 9 are not the same, so I can't really do anything right now unless I rewrite the 9. So usually we rewrite the bigger of the two numbers. So instead of 9, I'm going to write that as 3 squared. Okay, what happens is I've got this 2 in front of the x plus 7. So I'm going to change that to 2x plus 14. A lot of people forget to do the 2 times the 7 part of it. Now that we have the same base, we are allowed to drop those out and we can finish solving it. I'm going to get the x on the left side. Divide by 10, x is equal to 1.4. Now, if you do the Desmos trick, Desmos, what you're going to do is you're going to say y is equal to 3 to the power of 12x, and y is equal to 9 to the power of x plus 7, and you have to find the x point at the intersection. And I don't know if that's going to be easy or not. So you may have to zoom out, zoom in. I don't know, but that's how you do it. All right, so question 18 is also a very typical question that you'll see on your ACT or the EOC for all students. There's only one base, so this looks very different from the last one. If you have that one base, you have to get the base isolated. So that means the 3 has to go. I have to divide by 3. Okay, the 3 is now gone. I have the base isolated. When you're at that point where your logarithm or your base is isolated, you have to swap forms. That's where people get lost. So it's going to be log base 2 of 16 is equal to 3t. Almost there. If you don't see log base 2 in your answer, you can go ahead and get rid of it. They all have log base 2. We're going to divide by 3, and when you divide, you have to divide the whole side by 3. And that actually matches D exactly. All right, question 19 is talking about population over a period of T years. So if you write down the formula, it seems as though we had an original population of 5,600 people. And we are, looks like we are growing because it's base E. And this is the rate up here. And it says it's asking us to find the population. No, when will the population reach 11,200? So we are looking for X or T. This is not consistent. It should say X or T. They should be the same thing. But either way, we're looking for this. I would just suggest go ahead and type into Desmos y equals 11,200. And then y equals 5,600 e to the power of 0.059x. Most of you are probably going to do it that way. If you are an honors student, you can do this by hand. Let me show you how to do that. So set it equal to 5,600. Then we're going to divide both sides by 5,600. That is 2. That makes it look much nicer. And then at this point, we have to change it to a logarithm. So since it's base E, I'm going to use natural log base E of 2. And then I'm going to divide by 0.059. And that, yes, it will take longer than typing in a Desmos, but you may not have access to Desmos. So I've got 11.7, which rounds up to be 12 years. All right, so in question number 20, if you look at your answer choices, these are exact answers. So sometimes Desmos can be handy and sometimes it can't. If you use Desmos and you found the value of t, you're going to have to convert all of these to a decimal, all of your answer choices, to figure out which one it is. That is doable. It just takes a longer time than solving it. So I'm just going to show you how to solve it. We are trying to isolate t, which means that the base attached to the t needs to be isolated. So that 5 needs to go. At this point, the base is isolated. I'm going to have to swap forms now. So I'm going to do log base 2 of 3 equals 8t. And then simply divide both sides by 8. It should look like this. If it doesn't have divided by 8, it could maybe have like times 1 over 8. But that is going to match B. Okay, question 21 is extremely important, and I've not really addressed it a lot in this lesson or in this chapter, but we need to talk about it. Each one of these are a certain type of function. So this one is quadratic. That is from chapter 2. This is linear. That is from chapter 1. It's quadratic because it's squared. This one's linear because it's x to the first power. And this one is chapter 5 because it is exponential. Okay, they're all growing. They're all increasing in some way. This one increases consistently because it's linear. Quadratic increases because it's squaring the number. But exponential, what it does is it just skyrockets up. Now, I'm going to tell you, exponential is always the fastest. If you're comparing exponential to exponential growth, you are looking for the larger of the two bases. That one's going to grow faster. If it's decay, you're going to look for the smaller of the two. That will decay faster. But if you're comparing it between quadratic and linear, this one's always going to be the fastest. The slowest is going to be linear. Okay, it's consistent, but it's going to be slower. And then, and when I'm talking about growing, I'm talking about like extreme values to the far right. So as x increases a lot, exponential is going to be the fastest. Quadratic is going to be the second fastest, and linear is going to be the slowest. So the slowest one is going to be g of, right here. That's the slowest one. It says which inequality is true for large values of x. That means that when it gets really, really, really big, what's going to happen? So almost like in behavior. And then the biggest one obviously has to be h of x here. So yeah, A is the only one that makes sense. So question 22 addresses this concept as well. It's basically asking you to compare it not with large values, but with a very specific x value of 10. But as long as you understand the concept, you can easily answer this question without really doing any math. So this 4x squared here, this is quadratic. Okay, and the 4 to the power of x, this is exponential. So clearly the exponential, as your x values get bigger, see how they're getting bigger as we move down the table? It's getting larger, which means that these values over here are going to take off. So while these are similar at first, these are going to get much bigger faster. So if you take a 10 and you plug it in, you can absolutely type that in your calculator. You get like 400. But if you type in 4 to the power of 10, it's going to be astronomically larger. So the value of f of 10 is going to be much smaller than the value of 4 to the power of 10. So that means f of 10, no, they're not equal to each other. Yes, f of 10 is definitely going to be smaller than g of 10. And that is it. So just please take your time, look over these. You do have several on your test tomorrow, and you're going to have some coming up at the end of the year. Thanks for listening.